Hey everybody, welcome back to another lecture video. This time we are going into chapter 6 on chemical composition. So, how much sodium? That's the question that we could ask, right? Sodium is an important dietary mineral. I think we've talked about that sodium, oops, that's not sodium. Just kidding. We've talked about how sodium is a part of sodium chloride, table salt, and that we need it for our biological functions. Mainly, sodium is important for establishing and maintaining an electrical balance across our neurons, the plasma membranes of our nerve cells and our brain cells to help um, send what we call action potentials or signals, basically how cells communicate to each other. It's involved in also the regulation of body fluids. If you eat too much of it, it can lead to high blood pressure. Now, the FDA recommends a person consume less than 2.4 grams of sodium per day. Now, this is 2,400 milligrams if you guys are paying attention to other prefixes. Now, the mass of sodium that we eat is not the same as the mass of sodium chloride that we eat. How many grams of sodium chloride then can we actually consume and still stay below the FDA recommended limit? So the chemical composition of sodium chloride, is given by the formula NaCl. And there's one sodium to every chloride ion. So one sodium ion, one chloride ion. Since the masses of sodium and chlorine are actually different, the relationship between the mass of sodium and the mass of sodium chloride is not clear from the formula on its own. And we need to calculate the amount of a constituent element in a given amount of a compound, and that would be the mass percent of that element in the compound. So that information isn't built into this formula. We have to take this formula and then figure that out. Now, the information in a chemical formula, along with atomic and formula masses, can be used to calculate the amount of a constituent element in a compound, like how much iron is in a given amount of iron ore, or how much chlorine is in a given amount of a chlorofluorocarbon. This is Freon 12. I don't think we use freons anymore. These chlorofluorocarbon emissions, I wrote that backwards. The more metal would be written first, it would be Cl2F2. Cl2F2. These guys tend to speed up the reaction of the degradation of ozone, and it led to, in the past, a hole in the ozone layer. So we don't really use these chlorofluorocarbons anymore, but we can still calculate how much chlorine there would be in a given amount. Now, the way that we're going to do this, we're going to make some analogies first, is essentially something we call counting by weight, or counting by weighing. And we can make an analogy here to if you were buying nails, right? You would buy nails, let's say, by the pound. Some hardware stores sell them by the pound. It's easier than selling them by the nail, or having to price out how much one nail would be. They just weigh them. So you don't have to necessarily buy a pound, but they would throw your nails on a scale, and then there would be a calculation that would figure out essentially how many nails you were buying. So this problem is similar to asking how many atoms are in a given mass of an element. So saying how many nails are in 3.4 pounds of nails is the same as saying how many carbon atoms are there in 8.25 grams of carbon. Now, let's say a customer buys 2.6 pounds of medium-sized nails, and a dozen of these nails weigh 0.150 pounds. So then how many nails did the customer buy? So we would say, okay, 2.60 pounds of nails, and we know that, this is a conversion factor here, that every dozen nails is 0.15 pounds. So we would set up our conversion factor so that pounds is on the bottom, so it'll cancel pounds on top. This number is right here. Now we're in the unit of dozens of nails, or just nails in general, but per the dozen. And then we'd have to convert that one more time. We'd have to say how many a dozen is, because a dozen is one of those words, right, that just means a number. I'm sure most of you, all of you, know that. A dozen equals 12, and a baker's dozen equals 13. Do you guys know what a gross is? Gross? It's a dozen. A gross is 144 of something. So these numbers, I'm sorry, these words just represent numbers, and there are others that you know, like century and decade, right? You know those words, and you know how many years they represent, but they are just placeholders for numbers. Well, we have another placeholder for a number that I'm going to introduce to you guys in a few minutes. I'll introduce the number to you in a few minutes, but the placeholder word is called the mole, or moles, just like dozen or dozens. So we'll get there. So, of course, you'd have to know a dozen is 12, or you'd have to look that up. But now in our problem, we've taken 2.6 pounds, we've converted it into some number of nails, dozens of nails, and then we've taken another step to say how many nails are in a dozen, because we could just stop here with our answer, but our answer would be in dozens. So the question would be, how many nails do you have? And let's calculate it. I've got my calculator here. We'd say 2.6 pounds divided by 0.15 pounds is 17.3 dozen, right? Dozen. Well, that's not helpful. So we want to know how many that is. So then each dozen is 12, and we do one more step on that problem, and we come out with, what is the answer here? 208 nails. So in this analogy, we're going to use the weight of the nails and then the fact that 12 is a dozen to get the actual number of nails. To show you how this is going to deviate when we talk about atoms, we're going to most likely use the grams, but you could see that we could, if we were given pounds, we could go into that. I don't know if you guys know that there are 16 ounces in a pound. Oops. LB, and then there are 28, give or take, grams in an ounce. You know, we would look up to write number of sig figs and so on, but if we were given pounds, we could go into ounces and then ounces in the gram. You could look up any direct conversion online. You could find how many grams there are in, a ton. Just Google it and you would get that exact number. I encourage you to do that. Science and being a scientist is not about memorizing things and knowing all these numbers by heart. It's about knowing where to look for the information that you need and, retaining what you use and leaving in a book what you're not going to use. Okay, so this differs from the atoms in that instead of pounds, we would normally start with grams. Grams, we're going to use a conversion to get us into something called moles, which we can think of like the dozen, where a dozen equals 12. A mole equals the number of molecules or the number of atoms. It could mean the number of people, just whatever you're talking about. We wouldn't talk about people with moles because, well, frankly, 1 mole of people would be so many people that it would be a ball of people bigger than the Earth. And I mean, so it's a bad number to use to talk about humans because there's A, not that many humans around, and B, it wouldn't even make sense to have that many humans around. So it's just a number it's a really big number, a giant number. And you can imagine we would talk about giant numbers of atoms, right? And not giant numbers of, mountains or people. Okay, so counting by weighing, or atoms by the gram, basically means that we're going to switch to what we call the chemist's dozen, the chemist's quote-unquote dozen, the mole. And the mole is equal to, 1 mole is equal to 6.022 times 10 to the 23. So it's a 6 with 23 zeros behind it. That's more than 100 billion trillion, and I think even with more zeros. So really, really, really big number. We can talk about moles of stars and moles of atoms and maybe moles of grains of sand, but it would be like 5. There'd be like 5 moles of grains of sand on the Earth. It's still a big number. So we call this Avogadro's number. Avogadro is the one who it's named after. 1 mole of anything is 6.022 10 to the 23 units of that thing. And I mentioned humans. What about kittens, right? A mole of kittens is a ball of kittens roughly bigger than the moon. To give you an idea, kittens are smaller, so it's only bigger than the moon. But a mole of elephants would be like way bigger than Earth. Why are we thinking about elephants? Let's talk about something a little more easy to grasp. How about a mole of marbles, right? 6.02 10 to the 23, or a mole's a grains of sand, 6.02 10 to the 23. But with a bunch of atoms, it's actually a little more visually easy to see. So 10 to the 23 moles of copper atoms, 6.02 10 to the 23 moles of copper atoms, can actually be visualized in 22. I think that's where my numbers got mixed up in my head. 22 real copper pennies. When I say real copper pennies, I mean before 1982 or 1980. In the 80s, they switched to making pennies no longer out of copper. Copper is pretty valuable. It's worth more than a penny. So, it's a good conductor of electricity, of electrical components. I mean, it was underutilized when we were making it into pennies. So pre-1980 pennies are actually really made of 100% copper, and those you could get about 22 of them to have a mole of copper. Now, a mole of helium fits into 2 large helium balloons, approximately, right? 1 mole of helium. Helium is a gas in this state. Copper is a solid at room temperature. So the numerical value of the mole is defined actually as being equal to the number of carbon atoms in exactly 12 grams of pure carbon. So that would be carbon 12 and having exactly 12 grams of it. So, right, exactly, on and on and on, number of sig figs. So it's kind of a definition that isn't something we can actually put down and prove. I think they've actually switched modern, this last couple of years, switched from this being this being defined by a physical object to it being more defined by the laws of nature in some way. But I could be mixing that up with what they did with the kilogram also recently. Okay, so this relationship allows us to weigh these atoms, or the weigh the elements, and then as such to count the atoms. All right, so let's before we move on, let's try a calculation. So let's convert moles to atoms using the Avogadro's number. So let's start with something that we just looked at, some helium. Let's take 3.5 moles of helium, and let's find out how many helium atoms that is. All right, so we need to get the relationship here, moles to atoms. So 1 atom is how many moles? Just kidding. 1 atom would be 6.02 10 to the 23rd of a mole. That's not what we want. So we'll just say it this way. 6.02 times 10 to the 23 atoms is equal to 1 mole, rather than to define how many moles 1 atom is. But again, it would just be an inverse. It would be 1 over that number. Okay, so we've got moles and we've got atoms. So we're going to start our calculation with 3.5 moles of helium. We need to set up this conversion factor with moles on the bottom. 1 mole helium, Avogadro's number on top of atoms. Remember, a mole can be of elephants, so we need to define that it is of atoms here. And then units should cancel. And our answer, this is a good opportunity for you to pause the video and put this into your calculator and try it for yourself. Common mistake that students make And maybe it won't happen here because it's multiplication, but if we were dividing, like if we were going from atoms to moles, you would have to divide by 6.02 10 to the 23. And what most students do is they don't put parentheses around this number in their calculator. So their calculator first divides by the 6.02, and then it thinks it's done dividing, and it multiplies that answer by 10 to the 23. And you would do your calculation twice and get that same wrong answer twice. And so then at the end, you need to make sure your number makes sense. Okay, so we'll check to see if my number makes sense here once I'm done doing this. So the answer comes out to be, when you do the math, 2.1, we're keeping the right number of sig figs, times 10 to the 24 helium atoms. And does that make sense? It should. It should. 1 mole is only 10 to the 23, and we've got several moles. 10 to the 24 makes sense. It's a bigger number and not a smaller number. That's all the analysis we need to put into it. Does the number make sense in the size of it? Is it bigger or smaller the way it's supposed to be? Okay, so that's converting moles to atoms. Let's try an atoms to moles. So let's take 1.1 10 to the 22 silver atoms. Now you could probably already look at this and decide how many moles this is going to be. Is it even going to be 1 full mole? It's not even as big as Avogadro's number. So it's unlikely that we'll even have a full mole here. So we're going to say 1.1 10 to the 22 silver atoms. We're going to say there's an Avogadro's number of atoms of any type. You don't have to write the silver here. You get into a good habit if you write silver atoms, because later when we're dealing with multiple elements within one equation, then you'll know which atoms you're actually referring to. So it's a good habit to get into. Is 1 mole of silver. Here's where you want to pause the video, see the answer for yourself, and then see if you get the right answer. If you divide this properly, you should end up with a number that is less than 1 mole. But if you do this improperly, you're going to get a number that is much, 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 much bigger, right? It's going to be something like 10 to the 23 moles. It's going to be that big, which is totally wrong, right? It can't even be. That's an illogical answer. So that's what I mean by check them. This will be 1.8 10 to the minus 2 moles of silver, or 0.018 moles. That's what your calculator would have said if you don't have it set to scientific notation. All right, so these pictures have the same number of nails. They both have a dozen. Now, clearly one is bigger than the other. This is the same as what we have with elements. We can have the same number of atoms. Both of these are 1 mole of substances. We've got 1 mole of sulfur and 1 mole of carbon. But you can see that they definitely have different masses, different weights. Now, let's talk about the difference between molar mass and atomic mass. So a molar mass is the weight of a mole of a substance. So molar mass is usually given in grams. You can see both of these shown here are the molar masses, 1 mole and grams. Now, what if we don't want to talk about how much 1 mole of carbon is? What if we want to talk about how much 1 carbon atom weighs? Carbon atom. Well, then we would say it is 12.01 AMU. So atomic mass is going to have the same number as molar mass, but it represents 1 atom as opposed to 1 mole of atoms. So let's switch it and talk about copper. 1 copper atom has the atomic mass of 63.55 AMU. 1 mole of copper has the molar mass of 63.55 grams. So you can usually tell by the units what you're dealing with. whether it's grams per mole or atomic mass units. Okay, so the lighter the atom, the less mass that 1 mole of that atom would have. We can convert between grams and moles the same way that we convert between moles and atoms. We just need to have a conversion factor. Now, these conversion factors can come from anywhere. We can get them from something like a relationship that we can see. So chemical formulas, for example, are conversion factors. You can see here in this 3-leaf clover that we could make the conversion factor that there are 3 leaves to every 1 clover. And therefore, if I had 9 clovers and I wanted to know how many leaves that was, we could use the conversion factor that 1 clover has 3 leaves, right? Hence 27 leaves. You can do that with spiders, legs per body, chairs, right? Legs per chair, steering wheels in cars, right? 1 steering wheel per car, 4 tires per car, 4 tires per 1 steering wheel. You could even make those kinds of analogies. We could say that there are 2 front legs for every 2 back legs. Anyways, the point is, we're going to get conversion factors from molecules as well. Before we go any further into the conversion factors of molecules, let's back up, and before we move away from the idea of grams into atoms, let's do an example, just one, of converting from grams to atoms. The reverse would be also true. So you can go from atoms or moles into grams, just as we can go from grams to moles or atoms. So let's go from grams to moles. We're going to need the periodic table, because we're going to be given 0.58 grams of carbon and asked to find out how many moles that is. So we're going to need a conversion factor. Now, if you go to your periodic table, you should have one inside of your book. You can see that 1 mole of carbon, if you look up carbon element number 6, the atomic mass, to less digits than you would see if you looked it up, is 12.01 grams. We wanted to arrange it this way so that grams will be easily cancelable and that the only unit we'll have left will be moles. You plug this into your calculator and you should get 0.048 or 4.8 10 to the minus 2. I mentioned that you can go back and forth. You could start with moles and figure out how many grams there is, or you could take grams all the way to atoms. I encourage you to take 16.2 grams of aluminum and tell me how many atoms of aluminum that would be. And the intermediate will be the moles of aluminum. So first figure out how many moles of aluminum there are, and then figure out how many atoms of aluminum. You can pause the video, give that a shot. I'll throw in this number for you, 26.98 grams per mole. You can fill in Avogadro's number and then give it a shot. I'll give you the answer in 3, 2, 1. So you should be able to do these types of problems and back again. Start with this number of atoms and calculate how many grams of aluminum it would be, and lay it out and show your solution map, and give yourself a chance to practice these problems forward and backward. Okay, so for compounds, the molar mass is the mass of 1 mole of molecules, or formula units. So molecules, of course, being like compound, non-metals, usually formula units is what we call ionic compounds, since they don't contain individual molecules. There's a chlorine and a sodium, and a chlorine and a sodium, and a chlorine and a sodium, right? Arranged in these crystals of repeating pattern, right, cubes and whatnot. So a formula unit is just the simplest ratio, so one of each atom. So that's what we would use to calculate the formula unit of, let's say, NaCl. Okay. The molar mass of compounds in grams per mole is equal to the atomic mass units, and converting between moles and grams is just the reverse of going from grams to moles. So let's try molecules. We haven't done a molecules one. We did do one with an atom. That's the easy version. So let's try a molecule one. So let's say that I have 4.78 times 10 to the 24 molecules of NO2. And I want to know what the mass is. What is this in grams? So we're going to need to take molecules, MLCS. We're going to need to take molecules to moles, which we can do using Avogadro's number. And then we can take moles to grams. Now let's lay out what we know. Avogadro's number is that there are 6.022 10 to the 23 molecules, or elephants, or whatever, anything, in 1 mole of NO2. Now, for the other conversion, moles to grams, we do know that 1 mole of NO2 contains 1 mole of N and 2 moles of O. So if you look at the periodic table, you add 14.01 plus 15.999 plus 15.999, you get 46.01 grams. Now remember, calculating molar mass was a subject of an earlier chapter. You guys should be practicing this and getting better at it. Of course, at home you could look up molar mass of NO2. That's why you won't see a lot of those types of questions on the exam, right? What's the molar mass of NO2? Well, you could just Google that very quickly, and there's no way that I can ensure that you're having to calculate it yourself, unless I cut you off from the internet completely. But yeah, I don't want to do that. So let's do the math. Actually, you guys do the math. I've just helped you set it up. Let's make sure that these are written the right way. They're not. This conversion factor needs to be flipped, right? So that we can use this number and cancel molecules out to get just moles. And then moles is also needing to cancel out to get grams. So these two conversion factors are not laid in here properly. But if you do the math, you should come out with 365 grams of NO2. So try that for yourselves. If you can get that answer, great job. Do a few more problems and then do them backwards. And if you've got that down, then I think you'll be great for the test. And plus this information, the ability to do this is going to be required by Chapter 8, where we're doing stoichiometry, that just to get the problem started, you have to do a mole to gram conversion. So, and not just for one molecule, but for every product and reactant inside your equation. So get used to doing these types of problems. Okay, so let's talk a little bit more about converting between moles of a compound and moles of a constituent element. Because at the moment we've done atom to essentially mole to essentially grams, and moles we can see can also be molecules to moles and moles to grams, and all of these would have backwards arrows as well. But what we haven't done so far is moles to moles. We can do grams to grams. That's a percent mass thing. I don't know if we've done percent mass yet. We did actually talk about percent mass in the last chapter, but we didn't use it in calculations. So we'll go over that. So we can talk about mole to mole. So what we can see here from this water equation, or this water formula, is that there are 2 hydrogen atoms to every 1 oxygen atom. So there's a few things that we can say. We can say there are 2 H's to every 1 H2O. we can say that there are 2 H's to every 1 oxygen, right? We can say that there's 1 oxygen to every 1 H2O. I think that's about all we can say for that. Actually, there's another one. There are 3 atoms to every 1 molecule. So just like we can make up whatever true relationships that we want, we can use these in calculations as well. So let's look at an example. Actually, before we look at this is mass percent. Let's do an example. So let's convert between moles of a compound and moles of an element. So find the number of moles of O in 1.7 moles of calcium carbonate. Okay, so we need a relationship here. We need a relationship between moles of calcium carbonate and moles of O. So you should be able to look at this equation and say something like every mole of calcium carbonate has a mole of calcium. Don't get caught up on the moles. Remember, if this was dozens, you guys would have no problem with this. If I said you have 1 dozen calcium carbonates and then said, how many calciums do you have? You'd say a dozen. And if I said, how many oxygens you do have? You'd say 3 dozen, because a dozen to you means a number, and you know that there are 3 oxygens inside every one of these molecules. That kind of math is easy to you guys because of the word dozen. Substitute it with moles and suddenly everything's confusing. It shouldn't be. A mole is just a bigger number than a dozen. But it still has 1 mole of calcium every time we have 1 mole of calcium carbonate. There's 1 mole of carbon every time we have 1 mole of calcium carbonate. So every 1 mole of calcium carbonate is 3 moles of O. So then we should be able to say, in an easy math equation, 1.7 moles of CaCO3, conversion factor, 1 mole CaCO3, 3 moles of O. Moles of calcium carbonate goes away, 1.7 times 3, 5.1 moles of O. Let's try another one. How many, let's see, 15 grams NaCl. How many grams of Na? All right. So this one we're going to have to go from grams of grams of NaCl into moles of NaCl, moles of NaCl into moles of Na, and moles of Na into grams of Na. It's doable, right? So what do we know? We know 15 grams NaCl. How do we get to moles? Easy. We look up on the periodic table what the molar mass of Na and Cl together are. We add them up. That is 1 mole of the formula unit NaCl. Now, how many moles of Na are in a mole of NaCl? That one's easy. 1 mole of NaCl contains 1 mole of Na from our balanced formula. So if your formula was wrong, then all of this would be wrong. 1 mole of Na now weighs, according to the periodic table, 22.99 grams. Grams of NaCl goes away. Moles of NaCl goes away. Moles of Na goes away. All that's left is grams of Na. 5.9 grams of Na. So this is how we would go from grams of a molecule into grams of an atom in that molecule the long way. Now there is a shorter way, And I want to show you guys that shorter way. So let's say that we have a different molecule here, CCl4. And we know that every molecule of CCl4 contains 4 moles of Cl. I guess I shouldn't call this a molecule. Every mole of CCl4 contains 4 moles of Cl. Every molecule of CCl4 contains 4 atoms of Cl. So atoms are to molecules as moles are to moles. Now the relationship inherent in the chemical formula allows us to convert between moles of the compound into moles of that substance. And if we know the weights of these things, we actually have a relationship between the masses of the compound and the mass of the substance. We call this the mass percent composition, or mass percent. And we would just calculate it like this. We would find the mass of X in this case. If we wanted to know the mass percent of chlorine in this compound, we would get the masses of all 4 chlorines, and we would put that over the mass of the entire molecule. And then we'd go times 100. Let's see, do I have a example? I think I have an example. So let's say that I have, well, actually, let me tell you how we find mass percent. So how do we find mass percent? How do we calculate this stuff? So let's say that we have a 0.358 gram sample of chromium, okay? And this reacts with oxygen. So it reacts with oxygen, and it forms 0.523 grams of the metal oxide. We don't really know the formula because we don't know the oxidation state of chromium, but let's just say that it's CrXOY. They form some kind of compound together in some ratio that we don't know, but we know that we can weigh them. And from that, we know the weight of the chromium and we know the weight of the final product. So we could stick those numbers in here, and we could say the mass of the chromium is 0.538. The mass of the compound, the metal oxide, 0.523 grams. Let's just call it metal oxide. We say times 100, and we'd get, this is 68.5% chromium. So what we know now about this metal oxide is that it's 68.5% chromium, and we can use that as a conversion factor. We can use it as a conversion factor. Let me give you an example. I'm going to use a different conversion factor now. So let's say that we know sodium in sodium chloride is 39%. So sodium is 39% of the mass of sodium chloride. So what this allows us to do is to say that for every 39 grams of sodium, right, because percent means 100, cent is 100. So 39 out of the 100 is sodium. Now we can make this however we want. We could say 0.39 grams out of 1 gram. We could say 3.9 grams out of 10 grams. Whatever still is 39%. But it makes the most sense to just make these out of 100. So 39 grams of sodium to every 100 grams of sodium chloride. We could use this in any ratio. We could say there are 39 grams Na over 100 grams NaCl. We could say that there's 100 grams NaCl over 39 grams Na. Well, how would this be useful to us, right? But didn't we just do, in a previous problem, we figured out what the weight of sodium would be inside a particular amount of sodium chloride? We could have done that problem much easier. In fact, we can actually use this answer to solve the FDA problem from earlier. So let's do that. So the FDA had said 2.4 grams of sodium is the recommended daily amount. The question for us is, how much sodium chloride can you consume and still be under that or at that limit? Since we know now that it is 39% Na as far as sodium chloride, we can do a conversion. So we know that we have 2.4 grams of sodium that we're interested in eating. We want to know how much sodium chloride that translates to. we know that for every 39 grams of sodium, we would have to have consumed 100 grams of sodium chloride. This is going to cancel our units. We do a quick calculation, and we would have to consume 6.2 grams of sodium chloride in order to consume the recommended daily amount of sodium, 2.4 grams. So mass percent allows us to quickly convert between the weights of things without having to go into the moles. That's what we did the first time. We took the grams of one of these, we took the grams of this, went into the moles of that, did a mole to mole conversion, and then a mole back. All right. Now, the mass percent composition is based on the chemical formula. The mass percent of the element, like let's say chlorine in this top compound, because there are two amounts of chlorine, you have to account for that when you do the mass percent. You can't just take the mass of chlorine on top and the mass of the whole thing on bottom. You have to account for how many chlorines you're talking about. And that's important for the whole molar mass as well. So the chemical formula will help us get the mass percent. And so here, this is a typical calculation. What is the mass percent composition of chlorine in carbon tetrachloride difluoride? And so we would have to add up all of these things. Now, we can do that problem. We would just need the masses. So chlorine, I believe, has a mass on the periodic table about 35. So 4 times that comes out to be just about 141.8 grams. If you add a carbon and 2 fluorines in there, we get the other mass in here, 203.8 grams. If you multiply this by 100 after you do the division, you get 69.58%. So this would be 69, roughly 70% chlorine. And that makes sense. Chlorine is the heaviest element within this compound. Okay, there is some chemistry health relating to fluorine and fluoridation of drinking water. I don't know if you guys know that fluoride strengthens tooth enamel, actually helps prevent tooth decay, but too much fluoride can actually cause teeth to become sort of disease-looking, brown and spotted. It's called a dental fluorosis. And then extremely high levels lead to this happening on your bones, skeletal fluorosis. But at certain levels, there is a general consensus that between 1 and 4 milligrams a day of fluorine can actually have, some health benefits. And so if you drink water that has fluorine in it, then you benefit from that. Fluoride is also added to toothpaste to help with your teeth. Now, it's often added into water as sodium fluoride, NaF. And you could calculate what the mass percent composition of the fluorine is in sodium fluoride. And you can also calculate, let's say, how many grams of sodium fluoride you would need to add to 1,500 liters of water in order to fluoridate it at a level of 1 milligram per liter. So the question would be, to 1,500 liters, how many grams of NaF would you have to add, right? This is the kind of calculation that a scientist who works at a water treatment facility would have to do to know how much sodium fluoride to add to the water. So let's switch gears though and talk about how we actually get our empirical formulas from chemical formulas or from mass percent compositions. So to remind you, an empirical formula is the simplest whole number ratio of each atom in a compound, but not the actual number of each atom in a compound. Now, the molecular formula is always the whole number multiple of the empirical formula. So if we have the empirical formula, which is the simplest ratio, we can multiply it by a whole number and actually get our molecular formula, which is the real thing. I'll give you an example of that. If we have CH2O. CH2O is the simplest whole number ratio of the atoms in sugar. But that's not what a sugar molecule looks like. We need 6 to multiply that by 6 to actually get a sugar molecule. The real formula for a sugar is C6H12O6. So molecular formula differs from the empirical formula. Now, the only way we can get a molecular formula is by figuring out what the empirical formula is and also knowing information about the masses. So let's look at how we get that. So one of the first experiments that we can use to get chemical formulas is called decomposition. And this is an electrolysis experiment where they're using electricity to actually split the H2O molecule into separate O2 and H2 gas. We can decompose a sample of water in the lab and find that it produces 3 grams of hydrogen and 24 grams of oxygen. So how would we use the 3 grams of hydrogen information and 24 grams of oxygen information to get the empirical formula? Well, the first thing we would do is we would divide them by their molar masses. So for hydrogen, the molar mass on the periodic table is 1.01. 1.0079, it's more than that, but roughly using this number of sig figs, it's about 1 gram per mole. And for oxygen, the 24 grams of oxygen at 16 grams per mole, or roughly 15.99, rounding, we divide those numbers to figure out how many moles we have, right? That's what you do, grams into moles. We just spent time doing this. So grams into moles. Once we know how many moles of each we have, okay, if there's a whole number already, if these are whole numbers, then we're at our empirical formula. But these are not whole numbers, right? We can't have, we can have 1.5 moles of oxygen, that's fine. But we can actually do a little trick here that'll get us to the real empirical formula. And that is, we can reduce these. We want to see what the numbers are in relation to like whole numbers and not partial numbers. I don't want to know how many hydrogen moles there are to 1.5 moles of oxygen. I want to know how many moles of hydrogen there are to 1 mole of oxygen. So if we divide both of those numbers by the smallest number, in this case by 1.5, we will reduce those numbers into whole numbers. And then we can see what the formula would be. It would be H2O1. And we could write that H2O1, or water, right? So this is how we use this information. So I think I might have given you some rules here. So there's a couple of different ways that we go about actually calculating mass percents. Calculating an empirical formula. But it always starts with either getting the given masses or given mass percents. You would always assume a 100-gram sample if you're given mass percent. So if they say something is 11% and 89%, this or that, just turn these into grams. Just say it's 11 grams and 89 grams. That makes it much easier. Dealing with 100 grams total eliminates the use of the need for having to have percent numbers. Second step is to turn your grams into moles. Third step is to kind of look at that. If you have some whole numbers, or what we did here is this is the pseudo formula, right? H3, H3 to O 1.5. That's the pseudo formula. So over here it would be H3 to O 1.5. Now we don't want that, so we divide those by the smallest one. So both of these get divided by 1.5, and that gives us the better numbers, the H2 and the O. Now sometimes we still do all of these steps and we don't have whole numbers here. When that happens, we might have these kind of numbers. We can multiply everything by one of these subscripts. So for example, what if we ended up with C4O 4.25. So even though we divided already, we did all the steps, this is what we end up with. So we can see here that since one of our numbers ends in a 0.25, if we multiply by 4, we'll get rid of it. So everything by 4. That would give us C16O17. That's how we take care of that type of issue. Let's do a couple of example problems before I sum up the review here. So first, calculating empirical data from reaction data. Let's say you can be given data like this. 3.24 gram sample of titanium reacts with a 5.4, reacts with oxygen, let's say with some amount of oxygen, to make 5.4 grams of a metal oxide. So what's the empirical formula? So you have to start with the grams of each. How many grams of titanium? How many grams of oxygen? Let's just call it O. How many grams of O? You turn both into grams of O, both into moles. How many moles titanium? How many moles oxygen? Now, right off, you see that you don't know the grams of oxygen, but conservation of mass tells you that the total weight of this side has to equal the total weight of this side. So go ahead and give this one a shot. I'm going to give you the answer here in a second that you can check yours too. So if you find out the oxygen mass, you should have found that out to be 2.16, and then you convert both of those to moles. And after you do that, let's see. Oh, I don't have my periodic table in front of me. Oh man. Well, actually, that's not the point of what I'm trying to show you right now. What I'm trying to show you are the different ways you get your data. Sorry, I went down a rabbit hole. You guys could calculate this and figure out the answer here. I'm pretty sure titanium oxide forms I'm pretty sure it's a 1-to-2 ratio, like this. But you guys would have to check that. I don't have the periodic table in front of me. So that's one way. So let me summarize. You can get reaction data. You can get TIXOY, we don't know the formula, but you can get the mass of that, you can get the mass of this, and not have the mass of that. But these are your two elements, these are what you're going to use. You can get percent data. You can be given data like this. You have a compound that is, let's see, what's a good example? 66% oxygen, 24% carbon. What does that come out to? 70, 80, 90, 10% hydrogen. So this is another way that you can get the data. What do? Convert all of these to grams. Just say out of 100 grams, 66 grams is O, 24 grams is carbon, 10 grams is H. So that's another way that you can get the data. I'm trying to think, this isn't Chem 1, so Chem 1 there's a few other ways, combustion and whatnot, that you have to worry about. We like to do that too. We like to take let's say that we have a compound that is let's say X, H, Y, O, Z. We don't know the formula. We want to figure out the formula. So we burn it, we combust it with oxygen. Remember combustion? And so this leads to carbon dioxide and water. Carbon dioxide, we haven't gone over this yet. This is like the next chapter. Carbon dioxide and water, and we can weigh these things. So let's say that we know 44 grams and 39 grams or whatever. We can't just add these together and figure this out because we don't know how much oxygen is added during combustion. So I'm just telling you what we would do in Chem 1. In Chem 1, we would use the information from CO2 to figure out how much carbon there was. We would use the information from the water to figure out how much hydrogen there was. And because these O's here don't come from necessarily this compound, they may have come from this compound, we can't look at those O's at all, but we can look at the weight of all of the carbons and hydrogens and compare that to the weight that we know was the starting mass, and we could subtract the C's and H's to get the grams of O. It gets more complicated, yeah. So you don't have to worry about that, fortunately. So you'll either get percent data or you'll get experimental data, or you'll just be told, how many grams of each thing you have. Now, once you've been able to calculate the empirical formula, the next step is the molecular formula. And remember, the molecular formula is just figuring out what the real number of atoms are. And the way we do that is the molecular formula is just the empirical formula times n. Okay, well, where do we get n from? N is the molar mass of the real formula, of the molecular formula. So this would have to be found out by some other experiment and provided to you. You would have to know that, and I'll give you an example. You would divide that by the empirical formula molar mass, which you could calculate. If we just figured out that something was H2O, we could actually calculate what the formula of that would be. For example, what would that be? CH2O is, I think, 30.03. 30.03. So we would stick that number in here. And you'd have to be given what the molar mass of the real thing was. Let's say it was given at 180.2 grams per mole. So we would calculate then from that information, the given and what we did. We would have to have started from scratch, knowing the grams, knowing the percentages, all of that work to calculate this formula, to then calculate this number, to stick it in here. Now, with those two given numbers, we could get n. N is 6. And now we know that the empirical formula, CH2O times 6, will give us our molecular formula, C6H12O6. So use the molar mass, which is given, and the empirical formula molar mass, which you calculate, to determine n. And then once you have n, you solve for the molecular formula. Okay, so in this chapter, we went over the mole concept. We talked about 6.022, 10 to the 23. A mole of an element is equivalent to the mass of the atomic. The mole of any element has a mass equivalent to its atomic mass in grams. So AMUs just use the same number for grams per mole. We talked about chemical formulas give us all kinds of relationships between numbers of each kind of element in a compound. They're based on the atoms or the moles. By using molar masses, we can convey information about the relative masses of each kind of element. The total mass of a sample of a compound can be related to the masses of the elements in that percent mass. And we looked at empirical formula and molecular formula, how we calculate them, where the data comes from, what it looks like. And if we're going to calculate the empirical formula, the molecular formula, we have to also know the molar mass of the compound. So that has to be able to be given to us. All right, guys. Here are some learning objectives. Hopefully this is helpful, and I will see you guys next time.